On April 10, 1912, the largest moving object ever built by human hands slipped into the Atlantic. A 46,000-ton masterclass in engineering, the ship was heavily publicized as an unsinkable fortress. Most historical accounts point to a single, massive force that doomed the voyage, a direct collision with an immense, immovable iceberg. But mathematically, the collision shouldn't have been fatal. The ship's lower hull was divided into distinct watertight compartments, a design specifically intended to absorb this exact kind of impact and keep the vessel afloat. To understand why those defenses failed, we have to look past the giant block of ice and focus on something incredibly small. The true culprit was hidden in plain sight, scattered across the entire vessel in the form of 3 million tiny iron rivets. These seemingly insignificant pins had one crucial job: binding the enormous external steel plates of the hull together under immense physical pressure. Deep inside those fasteners lay a microscopic chemical imperfection. That invisible defect would ultimately lead to the deaths of 1,500 people. Understanding this disaster requires ignoring the massive size of the hull entirely and looking closely at the chemistry of a single metal pin. Building a ship this scale was a race against the clock, forcing builders to make strategic compromises on materials across different sections of the vessel. For the center of the ship, where they expected the most stress, they used high-quality steel. But at the bow and the stern, the primary collision zones, they opted for standard wrought iron. The problem came down to industry grading. They sourced what was known as best-grade iron, rather than the superior best grade for these crucial structural areas. This diagram shows a cross-section of that lower-grade iron. The darker spots are high concentrations of slag, a glassy, brittle byproduct left over from the smelting process. At standard room temperatures, slag is mechanically stable. The builders couldn't detect any weakness as they pounded millions of these compromised pins into the hull. The fatal variable was introduced on the night of the sinking, as the ship sailed into the extreme 28-degree waters of the North Atlantic. This animation illustrates how the temperature drop altered the metal's internal structure. The intense cold reacted with the high slag content, stripping the iron of its flexibility and turning it entirely rigid. When the ship finally scraped against the ice, the hull met a massive, immovable force. Because the chilled metal was so brittle, it couldn't dent or stretch to absorb the blow. Instead, it experienced a brittle fracture. The frozen rivets instantly snapped under the pressure. The ice never actually pierced the thick steel hull plates. It simply provided enough lateral force to shatter the compromised fasteners holding them together. With the first few pins severed, a localized stress point was created on the outer hull. Looking at this simulation of the hull seam, you can see an unzipping effect. The failure of one rivet immediately transfers intense pressure to the next, popping them in a continuous line and forcing the plates apart. With the seams entirely separated, the ocean easily bypassed the thick steel armor and rushed directly into the lower decks. The engineering design meant nothing once the binding split open. The ship's survival threshold was a matter of strict mathematics. It was designed to stay afloat with a maximum of 4 internal compartments completely flooded. But that unzipping effect carried the breach down the side of the hull, exposing 5 compartments to the ocean and pushing the vessel exactly past its calculated limit. If the builders had used high-grade steel for those forward rivets, the seams would likely have held longer. A slower flooding rate could have bought the crew several additional hours, providing enough time for rescue ships to arrive. Resting 12,000 feet deep in the Atlantic, the wreckage remains a quiet reminder of how a tiny supply chain compromise doomed an engineering marvel. It forces modern engineers to scrutinize every small component in our infrastructure. What other massive human creations might be vulnerable to a single microscopic flaw? Let me know your thoughts in the comments and subscribe for more deep dives into history.